Hey, good morning, everybody. So welcome to the measurement session. My name is Alex Nooran. I'm from UC San Diego. It's my pleasure to introduce the next four talks. So the first talk of the session is about connectivity with low Earth orbit satellites. And it's being given by the first author, Zeci. He's an associate professor at Tsinghua, where he received his PhD in 2018 after spending a couple years at Purdue. And after graduating, he spent a couple years at Tencent before moving back to his alma mater. So with that, we'll get started.
Okay, thank you for the introduction, Alex. Good morning, everyone. I'm Zeci from Tsinghua University. Today, I'm very happy to introduce our very interesting work, LeoCC, making internet congestion control robust to LEO satellite network. So this is an outline of my presentation today. Over the past few decades, the internet has developed at an astonishing pace, offering us many ways to get connected through internet, mobile networks, Wi-Fi, and more. However, from a global perspective, internet penetration is only about less than 17%. That means a significant portion of the world's population still remains unconnected. For example, in the rural area, remote ocean, flights, and other places. The recent low Earth orbit or LEO satellite constellations has brought new opportunities for expanding the boundaries of the internet. Many leading companies such around the world are actively accelerating the development of their own internet satellite constellations, such as Starlink and OneWeb. Take Starlink as an example. Currently, Starlink has launched over 9,000 satellites globally, with more than 7 million subscribers around the world. So this figure plots the architecture of today's LEO satellite network. Broadband satellites constantly move, providing internet access service to ground users. Set user traffic generated from the terminal is transmitted via a dedicated satellite terminal to a satellite, then downlink to a ground station, to a point of presence, and to the terrestrial internet. So in this architecture, satellites move rapidly relative to Earth's surface. This is a characteristic we refer as to LEO dynamics in this talk. So this LEO dynamics introduces network instability to the entire LEO network. For example, this figure plots some of our measurements we obtained from the real Starlink network obtained in the New Jersey, Cebu, and Madrid. We can find that the link capacity can drastically fluctuate between 10 Mbps to 65 Mbps. Also, the RTT drastically change, and we can also observe some unpredictable packet loss. So to understand such impacts on the internet congestion control, we then conduct a measurement study in a real LEO network Starlink to understand the problem. First, we performed experiments in the real satellite environment running different congestion control algorithms, or we call it the CCA, between the satellite terminal and the ground-based cloud server. However, due to the highly dynamic and unpredictable nature of real satellite network environments, it's very difficult to conduct controlled experiments and to reproduce the results. So, to enable controlled and reproducible congestion control experiments, we also developed a tool to record the real network trace and replay them in our lab environments. This tool allows us to perform fully controlled and repeatable experiments and analysis. So let's look at the results. Because the real LEO condition drastically change, we run each CCA for many times, and each test lasts for more than 2 minutes to obtain statistical results. Let's look at the performance of different CCAs. The first is the loss-based congestion control and delay-based congestion. Where is Cubic and Vegas and Cooper? Okay, they're here. So we can observe that their RTT is quite low, but they suffer from very low throughput. So how about other CCAs? Let's look at the model-based congestion control, for example, the BBR. Okay, where is BBR? Okay, they're here. We know that there are different versions of BBR, and we can observe that for the BBR version 3, the latest version, it also suffers from the throughput degradation. But for the first version, BBR1, the first version of BBR V1, it suffers from the high delay. It always overshoots the link and suffers from high delay. So we also know that recently there are some learning-based congestion control. They have a utility to treat the network as a black box and regulate their sending rates. So where is the learning-based congestion control? Here we can observe that these are two representative CCA survivors and propose. They also suffer from the very high tailed latency. So let's look at the results in our reproducible environments. We can conclude that existing CCAs fail to balance delay and throughput in Leo networks. So this picture shows the results under the exactly same bandwidth link capacity. We can find that, as we have also shown in the real environments, QB copper cannot fully utilize the link capacity, and BBR version 3 also suffer from throughput degradation, and also we can observe the high delay in the virus. So let's think about the problem. We know that every congestion control algorithm relies on certain models and assumptions. However, the problem is massive Leo dynamic-induced network variations break the fundamental models and assumptions of existing CCAs. So to mitigate this issue, one potential way is to identify and filter out those Leo dynamic-induced network variations. So we ask the question, is there an effective indicator to help endpoints to distinguish Leo dynamically introduced performance change and guide congestion control? Our answer is yes. So let's look at our design. Before we introduce the details, let's look at the basic idea of our solution. On our further investigation, we found that Leo satellite dynamics and the network change it causes are highly correlated with the frequent reconfiguration of satellite connections. So what is Leo reconfiguration? Due to the continuous movement of satellites, satellite operators need to frequently reconfigure their inter-satellite and satellite-to-ground connections. For example, for Starlink, according to its official document here, global satellite connections may update it every 15 seconds on average. In addition, satellite terminals also provide an interface that allows the user device to extract some periodical reconfiguration. So here, this is a more intuitive result of the reconfiguration and network variation relationship. We can, as shown in this figure, we can see that the network capacity and RTT can be viewed as a function of the reconfiguration phase. Every time a reconfiguration occurs, both the link capacity and RTT may experience a sudden jump or goes down. However, within a reconfiguration interval, changes in capacity and RTT are relatively moderate and smooth. So these insights drive the design of our LeoCC. Okay, this is we call it a reconfiguration-aware congestion control. So this figure illustrates the basic architecture of our solution LeoCC. This is a reconfiguration-aware congestion control, and this design consists of two key components: a detector and a reconfiguration detector and a robust rate controller. These two components address the following two questions: how to accurately detect reconfigurations, and how should the endpoint or the sender effectively adjust the sending rates? Okay. Our reconfiguration detection approach is motivated by a key insight that when a reconfiguration occurs, an end-to-end connection can experience a brief outage. During this period, in-flight packets are either dropped or delivered to the receiver with significant delay. So here we have a metric, we call it response interval. That is the time difference between two consecutive responses. So let's look at the RI response interval relationship between RI and the reconfiguration. So this figure shows a result of the response interval over time in different locations. So here we probe the nearest pop every 10 milliseconds, and we can observe that when a reconfiguration occurs, there always be an outlier of this RI. So we can use a threshold-based mechanism to detect the reconfiguration in real time. So far, we can detect the reconfiguration. Then LeoCC involves a dynamic Leo bottleneck model. We know that any complex internet path can be modeled as a single bottleneck link with a bottleneck bandwidth and a base RTT. So let's look at the Leo network path. From a physical view, the network path may change from over time, and the corresponding logical view, we can treat that there is a sequence of network states updated by the reconfiguration. So here, this is our bottleneck model. Bottleneck bandwidth and base RTT is our function of time. And also, LeoCC incorporates two new states. We call it the dynamic cruise and the reconfiguration adaptation. For example, during a reconfiguration interval, this is the dynamic cruise stage, and it will regulate the standing rates. And on every reconfiguration, LeoCC uses the reconfiguration adaptation to quickly convert to the new network state. So let's look at the dynamic cruise state. It regulates the rate during reconfiguration intervals. It uses two bandwidth estimators. Look at that here. This is different from what did in existing BBR. So we have one aggressive estimator and one moderate estimator use a maximal filter and use a Kalman filter respectively. One important thing here is that LeoCC cleared the outdated measurement results in the last reconfiguration to optimize the bandwidth estimation. Similarly, we use a RTT higher bound and RTT lower bound use a range instead of a single value to estimate the current RTT range, because we can see that RTT bands in our real-world measurements, and we also cleared stale measurements in the last reconfiguration interval. So further, based on this network bottleneck link estimation, LeoCC then regulates the standing rate during the reconfiguration interval. Here we have two important metric rates. The first one is the target rate, which is calculated based on the aggressive and moderate bandwidth estimation. And the other one is the real standing rate. Right here, we just follow some idea just like BBR to generate burst and drain the burst period by period. And then in the adaptation stage, it will converge to a new state, limit the in-flight packets, and save the current target rate. And after outage, LeoCC starts from the saved target rate in the new interval. Okay, so this is a basic idea of our LeoCC congestion control. Then let's look at the evaluation results. Here we implement our LeoCC in the Linux kernel with the plug-in TCP API, and we build two environments to evaluate our system. The first one is a real network environment with 3 Starlink terminals provided out by our research partners, and we have several Oracle cloud servers allowing us to build connections over the Leo network. We also build a trace-driven, fully controlled experimental environments to replay the recorded Leo network trace in our lab environments. Let's look at the results. First, let's look at the throughput and delay achieved in the live Starlink networks. Here we have the uplink results and downlink results. We also build experiments, including both the uplink and downlink in the right figure. Here we can observe that this figure, the left is better. So here we can also found that LeoCC achieves much higher throughput than Cubic, and about 5 times of the throughput of COPA. Also, it can achieve up to 85% higher than the BBR v3. Here, we also plot a Pareto frontier by connecting the intersection points of throughput and delay achieved by existing CCAs. Next, we show the results under the different path RTTs. For example, we use the same satellite terminal, but we choose different cloud servers. Some are close to the terminal, but some are very remote to build different path RTT. We can also observe that LeoCC can achieve the best throughput delay trade-off as compared to other existing CCAs in different path RTTs. So next, this is the results in our trace-driven testbed, because the previous one is in the real network. The real network conditions drastically change, and they are fluctuates. But in our trace-driven testbed, it's more determinable. It's okay. We can also observe the similar results that the LeoCC can achieve a better throughput performance trade-off than other existing solutions. Also, this is a time-varying throughput and delay results. We can show that over time. Also, we can compare with other systems, and LeoCC can achieve the better delay trade-off, delay throughput trade-off than others. So after the throughput and the delay, let's look at fairness. We use iPerf to run different CCAs to generate concurrent flows from the satellite terminal and to cloud servers. Here we look at the self-fairness. For example, we run concurrent LeoCC flows. We check the RTT fairness with the different path RTT, and also we look at the algorithm fairness. For example, we compared LeoCC and BBR. We can, as shown in this figure, we can show that LeoCC can achieve a good fairness here. Also, we have some results of showing the threshold. For example, because we use a threshold to detect reconfiguration, here empirically we found that a threshold of 45 milliseconds is good to achieve high accuracy for reconfiguration detection. We also show the results on application barrier benefits. Here we use the Dash server and to show that LeoCC can improve the video QoE compared to other kernel CCAs. And we also can show the results for the short flows and compare it in a conventional wired network environment. Due to time limit, we encourage you to read our paper for more details. So finally, let's conclude our work and envision some future work. In this work, we uncover the performance challenges facing existing CCAs in emerging Leo networks and identify the root causes. We design and implement LeoCC, a novel CCA that is robust to the drastic Leo network conditions. Then we conduct extensive evaluations and compare LeoCC and other existing CCAs in both real network and in our lab environments. And our results show that LeoCC can push the Pareto frontier and achieve the best throughput delay balance in Leo networks. Also, we have released the code and our trace. And for more details, we encourage you to read our paper, download the code, and use it. Thank you very much.
Thank you for the talk. Questions? So we got a couple down here. While they're getting the mic, I have a question for you. Listening to your talk, I couldn't help but think that there's a lot of similarity to some of the congestion control for hybrid networks, so optical switched and packet switched networks. So did you look at whether any of the congestion control protocols that were designed for those sort of environments might function well in this environment as well?
In our experiments for example, existing, maybe, for example, TCP runs similar to Quick, but for other congestion control algorithms, maybe the BBR version 1 is better than other existing algorithms because it uses a very aggressive policy. It uses a maximum filter to decide estimate the current bandwidth. But when the real bandwidth drastically change, it will overestimate the available bandwidth, so it will always overshoot the link. It can achieve higher throughput, but it also results in very high queuing delay.
Very impressive work. It seems that LEO brings state transfer. So why not we use some learning-based approach and then treat the changing state as a condition? So this can avoid the design of too many heuristic rules.
Thank you very much for this nice talk. Actually, we haven't really evaluated the results of learning-based algorithms. For example, as you can see in our previous slides, we compare with PCC virus, PCC protocols, and Orca. But we found that it is really challenging for learning-based congestion control to learn the utility function in the Leo network environment because both the bandwidth, packet loss, and the RTT can fluctuate very drastically. So it is very difficult and challenging to identify a good utility function for this kind of congestion control. You can read our paper and look at the results, and we also put them in our GitHub link. Thank you.
One more question.
Yeah, okay. Hi, Niels Aschenbroek, Osnabrück University. I wonder, in which kernel version did you implement it? Because it's not stated in the paper which kernel version you used. There have been recent advancements in the kernel regarding queuing and so on, so it'd be good to know which kernel version.
Like the 6 points, what, 1 or 2, I think. Let me double check it in our GitHub version link. But higher than like 6.
So I apologize, we'll have to take the rest of the questions in the break because I do want to keep us on schedule. So thanks again for the talk.
Thank you very much. We can talk offline.